Bismillahirrahmanirrahim. Welcome to Introduction to Electronics Season 3 Episode 6. Today we will focus about the topic. Let's see what are the topics for the today's episode. Topic discussed this episode will be number 1 transformers, number 2 some examples for the explanation for better understandings, and some problems as usual, and at the end we will also give some brief introduction about the rectification of the from diodes, as we already explained in diodes and application season 1 in details, but we will also give the brief introduction here in this video. Okay, let's talk about the first topic, that is the transformers. The voltage transformer can be thought as an electrical component rather than the electronic component. This is important thing, that this is the electrical component, not an electronic component. There are two types of the components. The main difference between them is their size. You can just find out their differentiate between these components by watching the size. The electrical component is those that are old components. For example, this is a simple transformer. The transformer is an electrical component as it has a weight as well and size, and it occupies size. But nowadays the transformers are replaced by transformer less power supplies, because we are already focusing our power supply continued topic from the previous episode, so we will focus on power supplies. So as you can see that another simple you can say that how we can identify the electronic component is that in nowadays computers, LCDs are used, and if we talk about their chips of the laptops as well as mobile phones, they are very complicated and their repairing is almost disabled. We cannot repair them easily. So these are basically electronic components that are installed by the computer assembly components. The electrical components can be replaced and repaired easily, and so the electrical component is the transformers. A transformer is based on the principle of the Faraday's law. Faraday's law is very simple, that if the current carrying coil, already that if there is a coil, for example this is a coil, let's say, I'm not good in trying, this is let's say a coil, and if there is this connected with some alternating source, alternating current is connected with this coil, then we can say this is a primary coil, and there is a jurisdiction, and it's an area of it is creating a magnetic field around it. And if the another coil that is not connected with the power supply or an alternating source, we can get a power supply, we can get induced EMF in the secondary coil. For example, this is another power supply. If we brought this another secondary power supply, if we brought this another secondary coil into the vicinity of its or you can say range of its magnetic field, then due to the changing magnetic field of the alternating source that is connected with the primary coil, we can get the induced EMF in the secondary coil. So this is basically used in this technique is used in the wireless power transmission nowadays on wider scale or huge amount of power supply, by just going in details, or you can say other methods by changing little bit methods, but we are basically focused on the transformer. So this is an old principle, and in case of the transformer, its function is basically in the as we are talking about the power supplies, so its basically function is to convert the 220 volt AC, that is basically 220 to 240 volt or 250 volt, that is primary our AC voltage. We are basically available all the time connected with the 240 volt. Whenever we want to reduce this, as in this case of the power supplies, basically we use a transformer. Transformer is number 1, transformer is secure. There is no connection of physical connection, there is no physical connection of the primary with the secondary coil, so it is secure. If for example it is failed, then there is no danger, it is not dangerous to the that it will damage the other components, so it is safe because there is no physical connection. Second disadvantage is that it occupies space and weight as well. So, and it's also costly as well. Now you can see from this point that there is no physical connection here. This is the physical this is a physical connection of the first coil, that is called the primary winding, and this is the secondary winding here on this side, right side. This is the secondary winding. Basically this V1 is this is not V1, you can say this is VP. P is written in the subscript as here replaced by 1. Basically it's VP, that is P represents primary, and here this V2 is, this is not a V2, this is basically VS, that is for secondary coil. And there are the number of terms same, you can replace N1 with NP, number of terms for the primary coil, and you can replace N2 for the number of turns in the secondary coil. Load is connected with the secondary coil always, and primary coil with the primary coil always. AC source that is coming from the outside of our home, that is connected with the coil A, or you can say primary coil. This is basically iron cores. And when you open a transformer, you will see a little bit different. This is basically when you open a transformer, this the situation is like if I am able to draw, yeah, there is a first primary coil, and here it is another secondary coil. This looks like a T. Basically this is a T, this is a T, and not this type of diagram, but in diagram it may looks little bit different, but it's easier to understand here. When it is connected with the power AC source, then this coil basically producing a changing in magnetic field. Changing magnetic field. The changing magnetic field travels into the iron core. This is an iron core, and this is a closed iron core. The flux travels in this direction is already available here. So by changing magnetic field in this vicinity of the second coil, that is secondary coil, we are basically able to generate some EMF here. So load is connected by rectification process as well as required. So here important thing is the ratio of the output voltage to input voltage is found to be equal if the ratio of the number of turns of wire in the two coils. This will ratio I will explain in the next slide. The power is called our input is equals to the power output in the transformer. It's called 100% efficient. So it's an ideal case if we are providing this input power in this I'm sorry, this is an ideal case if we are getting 100% output power, the combination of IV here in this in the output as we are providing the input. So basically in most of the cases 100% achievement is not available, as you know. It's an ideal case only. Important thing, this is the ratio that I was saying in the previous slide. Vs divided by Vp, it is basically voltage of the secondary coil divided by voltage of primary coil. This is the 240 volts, and this is the basically we are getting voltage V and put it here is directly proportional to number of the turns of the secondary coil divided by number of turns of the primary coil. Same is the ratio for the case of the current, but there is a change. This is directly proportional to the number of turns of the secondary, and this is inversely proportional. I will show you here. For example, this is the number of turns of the secondary. This is our secondary winding. That if you focus on this secondary winding, you can note that if we increase this number of turns of the secondary winding or secondary coil, you can our voltage on the secondary side is increased. Voltage is increased. We are basically increasing our voltage. If we decrease this number of turns, our voltage is decreased. So it's a direct relation with the secondary number of turns in the secondary coil. If for example for this we are getting 5 volt in our secondary side, Vs is 5 volt. If we increase, if we double, and for a while if we increase this winding by 2, multiply by 2, then our voltage is also multiplied by factor 2. So it will become the 10 volt. So it number of turns in the secondary coil is directly proportional to voltage of the secondary. Number of turns of the primary coil is directly proportional to number of turns. Voltage in primary coil is directly proportional to number of turns of primary coil. But here current in the secondary, here along this side, current of secondary coil is directly proportional to this side. Means to say in other words, current in the secondary coil here this side. For example, if we want to increase voltage, we basically we do here, we increase the number of turns. But when we increase number of turns, our voltage increase, but our current automatically decrease. This current factor is decreased because it is directly proportional to not this. It is inversely proportional to, sorry, it is directly proportional to this coil, not this coil. So if we increase its turn, its current is decreased, voltage is increased. Why this happens? Basically, if this not happen, then our Newton laws are basically failed, and this is not our ideal case. Power cannot be created. Okay, so this power is equals to IV. If we want to maintain the power, for example, the power we are this is 1 watt power supply, so we have to maintain. If we increase our voltage, current is decreased. This is the case we will do basically in generating station. In our step up transformer, we basically increase our voltage to 7,000 volts and kilo. That's why we call it basically kilowatt units. Kilo is basically 10 raised to power 3. So if we increase our voltage, for example, at this point, we in generating stations, we increase our voltage for the less losses in the transmission line, because power loss P losses PL is equals to I square R. Okay, okay, leave it. Power is equals to I square R. So if we increase our voltage, our current is decreased. If our current is decreased, here in power losses will be decreased because it is directly proportional to I square R. So if our our current is decreased, our this factor is decreased, it means our losses is decreased. So that's why we use this. This is basically the game of the number of turns. So explained. Power is equal to IV here explained. Okay, input power is output power. VP IP is equals to VSI. Yes, 100% in ideal case. This is there are some applications, for example, TVs, CDs, and video players, clocks, computers, radio, etc. These are the basically used when transformer is used to drop the voltage. It's ideal is not easy to achieve 100% efficiency, etc. I already explained. This is the first example, very easy example. In the particular transformer, the primary coil is wound with the 2400 turns. It means NP is 2400 turns, and the secondary coil is wound with 180 coils. It means that S is 180. You can imagine from here that if it is 2400, this is a simple idea. You can just make an idea from here. If this is 2400 turns and this is 180, it means that number of turns of there in primary coil is high and secondary is low. It means that obviously if the primary is 240, then we will get some lower on the value in the secondary side, because number of turns is low as compared to primary. If number of turns is increased, then our voltage also increase, as we explained in the last slide. So okay, if 240 volt, that is NP, is connected to the input terminals, calculate the output voltage, that is Vs. So this is the ratio as explained in the previous slide. So you can use this rearrange, and Vp goes towards, and it is multiplied by the Ns in the numerator, and this becomes this simple calculation, and therefore the output voltage is 18 volt. If you increase this number of turns here, you can also increase for your practice here, but change this factor, multiply by 2, and then you can see how your voltage is increase or decrease. You can just check yourself. A particular transformer is connected to the domestic power supply, that is again power supply. It is the VP 240 volt AC. If the required output voltage is 12 volt, that is Vs. You want it's fixed for 12 volt. Now it is fixed. Now we are going to select our number of turns. We are going to decide. That is basically company. What company basically do? Company basically manufacture when the transformer, they select their output voltage fixed. They fix their output voltage like this. If they want to create a transformer and manufacture a transformer 12 volt, what they basically do? They do that select. They fix this portion, that their Vs is fixed. Secondary side is 12 volt. Primary is 220 volt or 240 volt, and number of turns of their for example, in this case, number of turns of primary is fixed for 800. they want to select the number of turns of the secondary. So basically by using this calculation or this formula, they basically find there are 40 turns, for example, required. So they use the 40 turns for their transformer. These are some questions for your practice. I will provide you this file and you will definitely try yourself. Basically rectification is a process where we use our AC to convert our AC voltage to DC voltage. Basically there is a diode, and diode has a property, it allows to current to flow only one direction, that is called forward bias, and it does not allow to pass the current in the reverse bias state when the anode is connected with the reverse polarity. Anode is connected with, for example, negative, and cathode is connected with positive. I will explain here. For example, this is the rectification process. This is connected with the AC source. What is this AC source? AC source is like this. Okay, I will draw here. This is the AC source. Okay, in the half region it is have another polarity, and in the second half region the polarity is reversed. That's why we are called this alternating current. So for example, this is an alternating current. Let's say this is the first peak is right now for the first peak this is a positive and this is a negative. This positive, when reaches here, it is connected with the anode. This triangle, this side is basically anode, and this side is where the straight line is, it shows a cathode. So this negative reaches from this side towards the cathode, and this is positive reaches toward anode. What we will get basically in output for this first half cycle, we will definitely receive the output at the basically power supply, or you can say multimeter. The graph is available in this form, ignoring all the drops, for example 0.7 volt drops of the barrier potential, etc. I'm not going in details. If for example this negative half cycle, when the polarities are reversed, the positive is changed toward negative, and this is positive right now. The polarity is reversed. Now anode is connected with the negative, while this positive from this side is connected here with the cathode, reaches towards the cathode here, positive polarity. So this is reverse bias, and a diode cannot operate in the reverse bias. So there is we will not get any graph here. Diode does not allow to pass. So when again for the negative for the next cycle, when the positive half cycle appears, it allows current to pass. Then again graph is received, but this time for this case we are not getting in this particular region no output. So this is the basically graph as already explained. So if we change our polarity, definitely our graph will be also reversed. We will positive peaks are clipped off, negative are available, and in this stage. But this is not an good situation, that we are basically clipping off and lost our power in this region. So basically what we do, we use a full wave rectifier, that is called a bridge full wave rectifier, can be used in our DC power supplies. So this is a most achieved most good situation and used in the practical cases, and explained in the next slide. And we will get a full, you can see that here again and again there is no gap, no power is lost in this case. This is the situation. For example, let's again explain in details. For example, this is a case for this positive half cycle. This is a polarities. Let's say now this is a positive, and positive reaches towards this side. This is positive and this is negative. When the positive is here, positive is reaches to the D2. This is basically anode is connected with the here positive, and from this negative is basically here reaches to this side. So it means D2 is positive. So I shade it. This is basically positive. So when D2 is positive, it allows current to pass, while D1, at D1 you can see that this positive goes to here, but it this is the cathode of D1, so it does not allow to pass. So D1 is not in forward bias, it is in reverse bias. D2 is in forward bias. Now you can say negative. This negative reaches to D4, this is the anode, so negative to anode, this is reverse bias. So D4 is in reverse bias, I cross it. But now when this negative reaches towards D3, it is the cathode of D3, so it allows to current to pass. So negative reaches here, the current direction is from X towards the Y, that is from positive to negative. So this is the for the positive cycle. When the polarities are reversed, negative is here, this is negative and this is positive. Now what happens if I want to change the color from this here? Maybe is there available color? Where are the colors? I don't know. Okay, ballpoint is selected. Okay, I don't know about the selection of the colors. Maybe okay, this is the now negative and this is maybe positive. So what happens right now, this negative when reaches here, this is the D2 is connected in reverse bias. Now D2 does not allow to current to pass because this negative is connected to the anode of this, and this when negative is connected to this, D1 is now in forward bias. Now when there is a positive reaches to this side, this is now in reverse bias, so this does not allow to current to pass, this is in reverse bias. While this negative reaches to this, this positive reaches towards D4, that is anode, and it allows current to pass. Same now in this case, D1 and D4 for the second half cycle is D1 and D4 are in forward bias. So again this positive reaches to X, and from here this negative reaches to Y. Again current direction is same from X to Y. So these are the basically SMD components, as I was explaining in at the first episode. These are the electronic components. This is also electronic components. You can see that the 4 diodes are packed in a single packing and the size is reduced as well. Complexities are also reduced. These are nowadays used, and this is the explanation that I was explaining in the previous slide. By the use of the 41 and 4007 diodes, we can make a diode bridge. So this is the end of the season 3, though no episode will be coming in the next Monday, or you can say that this season is closed now, and we will explain other terms maybe next time and next year of further introduction, because introduction is not more appreciated by the students want more explanation. So we decided to close this season on the episode 6, and now I recommend you to watch Diode and Application season 1 and season 2 for details. So watch, learn, grow. See you next time.